All right, everyone. Thanks for coming to BrainMap. Welcome back from Thanksgiving break. Before we get started with Eugenio's talk, just a quick announcement. Between now and the next holiday break, we have some great BrainMap speakers slated for you. So on the 5th of December, Olivia Wiesmann will be talking about geometric cortical orientation and its effect on the fMRI volt signal. And then week after that, we have Vitaly Napadau. And then on the 19th, we have Clarissa Cooley. So 3 awesome talks coming up. Stay tuned for more details. For today, very pleased to welcome back Eugenio Iglesias. He's a Martinos Center alum, of course. He holds master's degrees in telecom and electrical engineering from the University of Sevilla and the Royal Institute of Technology in Sweden. He did his PhD at UCLA, and then he was a postdoc here at Martinos in the laboratory computational neuroimaging 2011 to 2014. He's now gone on to be a lecturer at University College London with a starting grant from the European Research Council. And presently he's visiting MIT and staying involved part-time here at Martinos. So with that, Eugenio will present building a high-resolution computational atlas of the whole human brain with histology, deep learning, and Bayesian modeling, free surfer implementation, and applications.
Thank you. Yes, I just wanted to have as many buzzwords as possible in that title. Yeah, thank you very much. I'm very excited to be back here. You'll see I've thrown a lot of stuff into this talk, and the reason is that you see there's an asterisk here, which means, well, I'm technically not at the Martinos Center yet officially, but I'm starting in 2 weeks. One day, essentially 20% of my effort. So if you guys see anything in this talk that you like, this is like pretty much a self-advertising type of talk, like, hey, guys, I'm back. If you want to work with me or do you like anything, let me know, because I'm really looking forward to resuming collaborations here, but also, thank you, starting new collaborations if you guys are interested. So yeah, let's start. So I'm going to first talk a little bit about why we want to do all this. Of course, the idea is to build this new atlas using histology, but I'm also going to give you a bit of history, how this whole thing started with work actually carried here at the Martinos Center, using MRI ex vivo and in vivo MRI data to build atlases. And then at one point, we decided to switch gears and move on to histology, which was great in many ways, but also introduced a lot of problems, which I will go through. At first, we just solved those problems by doing a lot of manual, with a lot of manual intervention, which was horrible and non-scalable. And then I will talk a bit about my work at UCL in London, where we are trying to essentially make this whole big pipeline fully automated and scalable. Okay, so in terms of motivation, we all know free surfer is cool. A lot of people in this room use it, right? The same goes for packages like SPM and FSL. They're not as cool though. But, and there's like, we've done like fantastic stuff with these pieces of software, right? Like in terms of like cortical analysis or parcellation, cortical thickness, subcortical structures, voxel-based morphometry, and so on. And this is all great. But the whole idea of our work has been to try to take this to the next level of detail. So I love this example, this print by my fellow countryman, Santiago Ramón y Cajal. This is over 100 years old now. It's a beautiful print of the hippocampus. I think they have a bunch of things in the MIT museum, actually. And if you look at the MR scan from ADNI 1, back from 2004, I can't believe it's been so long. The resolution is approximately, or the voxel size, 1.5 millimeter, cubic millimeter, sorry. And then you feed it through FreeSurfer. This is a coronal slice, and you get your hippocampal segmentation, which is great. There is plenty of cool stuff has been done with this type of segmentation. But now, if you look at like more modern, even within the ADNI, more modern scans, it's like, why wouldn't you acquire this beautiful, well, this is highly anisotropic, but still high resolution hippocampal scan and look at the subfields instead, right? I mean, we know from postmortem studies, animal models, even, well, Santiago Ramón y Cajal already knew like 100 years ago, right? That the hippocampus is not a yellow blob. It's got these substructures that have different connectivities. They are affected differently by disease, by aging, and so on. So All right. So the whole aim of this ERC grant is to build this. It has to sound fancy, right? There's the next generation set of tools for high resolution MR analysis. And at the core of these tools is this atlas we are trying to build using histology, which requires 3D reconstructing the histo of a bunch of human hemispheres. And then the idea is to take this atlas and build a bunch of computational tools that apply the atlas to the analysis of in vivo scans. It's still like early-ish. Though every time I update this presentation, I see this counter going up and I get a bit nervous. But so I can still say it's a bit early in the project, but hopefully I can show you some cool stuff. In terms of framework, I want to get this out of the way. We're still using these probabilistic atlases for Bayesian segmentation, Bayesian analysis of MRI data. At some point, maybe we'll have to switch to deep machine learning approaches. For the time being, we're still sticking to this type of approach where this is essentially what SPM does. And the advantage of these generative models of imaging is that they adapt in principle to any type of MRI contrast, arbitrary in principle, no matter if it's multimodal. So that makes it very interesting when you're going to distribute some software and you have no idea, or you cannot make any assumptions on the type of scanner vendor or field strength or type of contrast that that people are going to feed into the software. The other advantage of this type of Bayesian approaches is that, the main advantage is that if something goes wrong, you know why, so it's easier to fix. Sometimes with deep networks at the moment, I get the impression that all you can do is just throw in more data and hope for the best. But again, I suspect this is going to change sooner than later. Things where there's I don't know if Ahmad is here in the audience, but he's doing fantastic work actually, trying to do this type of segmentation with deep learning. So anyway, so going back like a few years ago, this whole building atlases with ex vivo MR, the probabilistic model that we have for segmentation is the following. So if you were to follow how data are assumed to be generated, you start from a probabilistic atlas that is encoded in this tetrahedral mesh. This is actually Koen van Glimput, who used to be my advisor when I was a postdoc here. It's Koen's framework. So you start with this atlas in a reference position. Looks like an abstract painting. You deform it according to a model. And then from this deformed atlas, you sample a segmentation. And from segmentation, you sample the image intensities. So you get something, if you were to sample the model, you would get something that looks like this. Is it very realistic or not? Well, probably not. But it turns out that when you solve the inverse problem, so you invert the model using Bayesian inference and say, well, if you give me an image and you give me the atlas, what's the most likely segmentation? This turns out to work pretty well. Of course, this requires building an atlas, right? Like for now, we're assuming the atlas is God-given, but what if you actually have to build it? So to do so, we were using ex vivo data. We started working on the hippocampus, and there was this beautiful data that was already acquired when I arrived at the Martinus in 2011. And the ex vivo MR was great, very high resolution. There is no motion, right? So you can throw your tissue block or your hemisphere for literally a weekend in the scanner, and you get these beautiful images. This is around 100 micron isotropic, where you can make very accurate delineations of substructures. If you use histology, same story, right? Like you can look under the microscope, you can use any dye you want, you can stain for different things, and you can make very pretty delineations. Of course, it takes forever because it's a lot of data. On the other hand, in vivo MR has the complementary advantages, right? So you have the whole brain, which is not always the case with histology or ex vivo MR. It's easier to label, and compared with histology especially, there is no geometric distortion. So the idea is, okay, why don't we combine both, right? It seems like the advantages of one are the disadvantages of the other. So they complement each other really well. So the ex vivo data looks like this. These are beautiful delineations that were made actually by a group of people. I think Ying is here. They're very, very, very pretty. This is actually a very good example where you don't have the field of view is limited to the hippocampus, right? So even if you wanted to label what's around the hippocampus, you wouldn't be able to do it. And if you look at in vivo segmentations, these were the manual delineations that were used to build the atlas in FreeSurfer. It's the other way around. So you you have like the whole field of view. You can easily label the whole hippocampus and the surrounding structures, but you cannot label the hippocampal subfields, right? But you can throw actually everything together in a modified model where you start from your atlas, same story as before, we deform it, we sample segmentation. And normally if you were to build an atlas, like for example in SPM, this is where you would stop. So you say, okay, you give me a bunch of segmentations like this, and then you use Bayesian inference to estimate the most likely atlas that generated these manual segmentations. In our case, we never have this, right? We never have both the hippocampal subfields and the surrounding structures. So we have to go one step further and say, okay, what we actually have is a version of this segmentation where all the hippocampal subfields have been like merged into a generic hippocampal label, if the scan is in vivo. And if it's ex vivo, it's the other way around. So I'm taking all the extra hippocampal labels and merging them into a single generic background. And then I can do exactly the same thing as before. So I can mix the in vivo and the ex vivo data, throw everything together, and compute the most likely atlas. And you get something that looks like this. This is going from anterior to posterior. This big blob is the amygdala. And here you start seeing the hippocampus. So paraceliculum, preseliculum, ceviculum, CA1 in red, CA2, 3 in green, and CA4. This atlas is represented as this sparse mesh that is like very, very fine in areas where you have like a lot of stuff going on, and very coarse and boring like in the background or the middle of the white matter. So once you have this atlas, you can apply it to segmentation. Like I said earlier, the advantage is that it doesn't really matter which contrast you have, if it's T1 versus T2, or even if it's both. It's actually very easy for multiple contrast because it's just replacing a univariate Gaussian by a bivariate Gaussian. So it's super easy. Also, something that happens in the ADNI dataset very often is that because this T2, this high-res T2, only covers a slab that is supposed to enclose the hippocampus, but sometimes the technician doesn't place the box properly, and you have like half of the hippocampus missing or the tail. That's actually not a problem because the only difference is that your Gaussian is univariating here and bivariating here, and you can still segment the whole thing. So that's very nice. In our old neuroimage paper, we compare with some manual delineations made by Susan Muller from UCSF, and we get like results that are more or less comparable, which is interesting. This is using T1 and high resolution T2. This is actually a very controversial topic at the moment, but also if you only have 1 millimeter T1s, you can still use the atlas. And we show that, of course, you cannot segment the subfields with the same accuracy that if you have a high resolution T2, because you don't have the internal boundaries, but you still get something that is useful. So for example, if you try to discriminate Alzheimer's versus controls in the ADNI using only the whole hippocampal volume versus the subfields, you get a bit of a boost in the classification performance. There is a bunch of other studies using the atlas, some of them with like a ton of subjects. So I encourage you to give it a shot if you're interested. This is all in FreeSurfer at the moment. And yes, this is blatant self-advertisement, like I said. More stuff that we did was extending this to the amygdala, which was, I thought made sense to put everything together in a single atlas because they are neighboring structures, right? You don't want to have an atlas for the amygdala and an atlas for the hippocampus, and then you run one, you run the other, and then the segmentations overlap, or they leave like a gap in between. You don't want that to happen. So this actually work mostly done by Zeynep Saygin and Dorit Kleeman, who used to be postdocs at MIT. And they made these pretty delineations of the nuclei of the amygdala. And then we can play the same game as before, where we say, well, this image that you're giving me, actually, I'm going to pretend that I did have all the hippocampal subfields labeled and all the surrounding structures labeled, but then someone came and merged all of those into a single genetic background. And I can, put everything together, all the data of the hippocampal subfields, the FreeSurfer data set, and these guys, and get an atlas that looks like this, where I get everything together, everything is consistent, and the amygdala is never in the hippocampus without, like I said, any overlap or gap in between. Again, you can we run this on the ADNI and showed that you can better separate Alzheimer's versus controls looking at the nuclei than if you use the whole amygdala. And the same thing in the ABIDE dataset, which is this autism spectrum disorder data. I don't know if you're familiar with it. I mean, in autism, the effect sizes are notoriously small, but you are able to pick up differences looking at the nuclei. More stuff that we added, because we're never going to stop, right? was these are actually only available in the development version of FreeSurfer, and it's not even published yet. So we have to we should publish this at some point. Is the separating the body and the head of the hippocampus. So you can also generate segmentations that look like this as well. We got some criticism with some of the internal layers of the hippocampus, which people said, well, it's impossible to segment that, even if you trust the prior. So we have a simplified version as well. Yeah, so you're very, very welcome to give it a shot. And like I said, I'm here now. So if you run into any problems, I'm here to help. We also extended this to longitudinal. So it's a bit of a different model, where we start from an atlas, same as before. We deform it according to our model. But now, instead of saying, okay, this deformed atlas is in the space of my subject, what we're going to say is that this is a subject-specific atlas, and we're going to further deform it to our time points. And this second deformation is much stiffer to reflect the fact that it's time points from the same subject. And then from this time point deformed meshes, you can sample the segmentations, from then sample intensities. So they are constrained to be similar to each other. And then again, you can use Bayesian inference to compute the most likely segmentations within this framework. So forcing this subject-specific atlas, which is obtained as a byproduct, to constrain the segmentations together. And you can show this is work with Martin Reuter, who also used to be, I think he's still appointed here, maybe, yes. You can show that if you compare the slope of essentially the atrophy slopes of Alzheimer's subjects versus controls, you can actually better separate the classes than if you only look at if you use the cross-sectional model, where you assume that each time point is independent from the others. So this is for the left hemisphere and the right hemisphere using the Myriad dataset, which is from UCL. Okay, so this was all cool. Everything was going great. But then when we started looking at the next structure, because that's essentially what I've been doing for a long time, well, like 10 years now almost, which was the thalamus. This was back in Spain. It turned out that using MR, it was very, very difficult to label the thalamic nuclei. And then we decided to move to histology. So this was work done in collaboration with Ricardo Insausti, who's at the University of Albacete back in Spain. And so I was talking to Ricardo a lot, and he actually visited a colleague in Germany. He did a lot of reading, and he said he was convinced that if we gave him the histology for the thalamus, he would be able to manually label between 25 and 30 nuclei. So we were very excited about this and decided to go for it. The problem, of course, is that when you take the tissue and you cut it into slices, block it, and section it, you lose all the 3D structure, right? So that introduces a whole new set of problems that, on the other hand, are also opportunities for research. So we decided to go for it. Something that we did, the first thing that we did was take this block phase photographs to assist the reconstruction. This was our incredibly sophisticated setup back in Spain, where we bought some stickers from the Chinese store next door and just put them on the microtome. Also this checkerboard pattern, which enables to correct for perspective. And then what you can do is that every time you cut a section, you can take a photograph, right? And using this checkerboard pattern, you can correct for the perspective to pretend that you took the photograph right from above. And then you can stack these photographs and you can create a volume. It's a weird volume because it's a photographic data, but it looks a bit like this. So these are coronal sections, right? So if you stack them and then reconstruct like an axial view, which is what you see here, this is what you get. So this photo volume, this block phase volume is not great, doesn't have a lot of contrast, but actually it has one big advantage, which is that because you take the photographs before you cut, there is no geometric distortion. So actually you can rigidly register this volume to the MR. Again, the contrast is not great, but because it's a 6 degree of freedom, rigid transformation, it works pretty well, actually. I don't know if you would agree with me. It's actually pretty good. And that makes your life so much easier than if you try to directly map the historical sections that are like heavily distorted in plane to the MR, because there's too many degrees of freedom. This is much easier. It's a very useful stepping stone, because once you've done this, you know, for each of these photographs, so essentially each horizontal line of pixels in this volume here corresponds on this image corresponds to a photograph, right? And we know the exact correspondence between photographs and histosections. So what you can do is take this MR, which is registered, and you can resample it to the planes of your photographs. So you end up with a problem like this, where you have, this is your block phase, this is your resampled MR to the plane of this block phase, and this the corresponding histology. That again, the correspondence between these two is deterministic. Like we know, again, which photograph corresponds to which section. So now you only have to register this heavily distorted histosection to this resampled MR slice. And at that point, I was in Spain, my fellowship was running out of time, and I thought like, I could spend, a lot of time, a lot of effort trying to come up with a method that does this. Or I can download a couple of audiobooks, put on my headphones and spend 2 weeks manually placing pairs of landmarks on them, like these red circles here. So I went for the latter because I wanted things to work. And I thought like, I can take care of the algorithms in the future if I revisit this problem. So I did that. The registrations look quite okay, in my opinion, especially around the thalamus. It's not perfect, but it's pretty good if you compare the two. Got it out of the way. And once you've done this registration, you can just essentially concatenate all the transforms. So from the histology to the block phase to the MR, go back to the original 3D space. And when you make manual delineations and bring them back to the MR space, you get something, you're very excited, like, yeah, great, I'm gonna have my 3D segmentations. And you get something like this, like, oh. But then you can, we came up with this little simple method to do smart interpolation. So we used a Markov random field that makes sure that you get a smooth segmentation at the end. Combine it with a Gaussian mixture model that makes sure that you look at the image intensities underneath when you decide how to interpolate these segmentations, and you get something that looks like this. It's a bit over smooth, but when you put everything together into an atlas, it's actually, it's actually pretty good. It's quite okay. It's more or less what you'd expect. And then we can do the same as before, apply the segmentation of in vivo data. You could argue that it's not, that great to try to fit this model to the thalamus here. Essentially what we're doing is looking at the mediodorsal and posterior nuclei, which are a bit darker in T1MR or brighter in T2, and then fit them. So if you look carefully, right, you more or less see this boundary here. So that's what we are trying to fit. It's not great, but it's not perfect. But actually, when you compare with other atlases based on histology, the volumes are more or less similar. The segmentations, again, they are robust to the input MR contrast, so which is nice because some of this actually data, thank you, Doug, for it. Doug sent it to me. Some of these sequences actually show these internal boundaries better than others. And it turns out, and I was very, very, very surprised by this, I still think there might be something going on that I quite couldn't figure out, which is that when you look at the volume of the whole thalamus to separate AD and controls in the ADNI, you are marginally better than chance, than flipping a coin. But however, when you look at all the nuclei simultaneously, your area under the curve is pretty respectable. It's 82%. And actually, it's the mediodorsal nuclei driving this. So I discussed this very thoroughly with Martina Boqueta back at UCL. Martina is essentially UCL's version of Jean Agustinak. And we're trying to figure out if it was maybe the third ventricle was growing and it's neighboring this nuclei. But even if you could argue if the third ventricle is growing and the mediodorsal nuclei, the boundary stays in the same place, then this nuclei has to be losing volume, right? So if you have any ideas, I'd be very, very interested in hearing that, yeah. Cool, so this was up and running, the whole thalamus stuff, but then we want to do the whole brain, right? And there is no way, I mean, I guess I can manually place landmarks for 2 weeks for a few thalami, but like for the whole brain, it's just not doable. So there is a bunch of things that we had to automatize. One was the registration of the block phase for the volumes, you will see in a minute. Another one was this 2D registration problem, and also the 3D reconstructions. And the other thing we haven't started yet, but it's actually the manual segmentation as well, because if someone is to manually segment like all these substructures, like in whole human hemispheres, it's just gonna be too much work. I think we had this email exchange last week where Song Lin, the guys from the Allen, right? Like they mentioned it took them, how long was it? 1.5 years, I think. Yeah. So we need to speed this up. So the first thing is the registration of the block phase photo volumes. So at UCL actually, so back in Spain, we were working with this frozen tissue, but this was actually, when we moved to UCL, this is a brain bank, and they do paraffin embedding. And then the problem is that your photographs don't have a lot of contrast anymore. So even the linear registration can be difficult. Luckily for us, because now we are doing whole hemispheres, it turns out that all the blocks constrain each other and make it a bit easier to register them, right? Because essentially, when you put everything together, you know that you have to have a whole hemisphere, and they have to fit with each other. So we came up with this. It's not super novel or anything, but it actually turns out to work pretty well, even though we're still fine-tuning the algorithm. It's a bit of work in progress, but the idea is that you want to optimize a loss function that is an average of some dissimilarity across your blocks. So this n here is essentially your blocks, which is 30 or 40 of them. And in addition to this dissimilarity, you normally have a regularizer. So this could be mutual information or whatever you want, or cross-correlation, whatever. And for this guy here, for the regularizer, the only constraint we have is that, well, the scaling factor of my block is expected to be at around, I think it's around 1.3, 1.4, which is the approximate shrinkage that you get because of the processing, right? The embedding. But then, and this is the new thing that we added, we included this term that essentially forces the pieces in your puzzle to fit with each other. So it turns out that it's actually very, very, very simple to encode this using this term here, which says, okay, if I look at every voxel and I sum so we have we have automated segmentations for the tissue in all these volumes, right? So if I take all those segmentations, which can be soft, they don't have to be hard, and I add the values from all the blocks on a given point, I expect that value to be 1, right? Because if I'm leaving a gap in between, then the sum of those masks will be 0. So I want to discourage that. But I also want to discourage overlaps, right? But if 2 blocks are overlapping or 3 blocks are overlapping, then this sum will be 2 or will be 3. So you also want to discourage that. So all you have to do is to penalize the deviation from 1. And in synthetic data, that turns out to work very well. So if I pretend that my T1 is my MRI and my T2 is my histology, and I just mess it up, if I register one at a time, it does something, but it's far from perfect. You have like sometimes big errors like this one here. And then it works much better if you include this term in the registration, or if you show the rendering, you start from here, and instead of getting this, you can get that, which is nicer. It's still work in progress, like I said. As we speak, actually, my this postdoc hired by this project is working on it on the real data. He's having a bit of problems, but hopefully in the next couple of weeks we'll have something ready to submit. Cool. The other thing, or one of the other things, is the 2D registration, what I talked about earlier. Like placing landmarks is just not an option. So back in the day, we submitted this paper to MICAI. I believe actually Bruce was the senior author in the paper, where we were showing that, okay, if you have this multimodal registration problem, let's say you have a PD volume, you want to register to a T1. So Plan A is using mutual information, and that works very well when the problem is rigid or linear, but non-linear, it blows up very quickly. So actually, you are better off if, and this is a big if, but if you have a database of matched T1 and proton density volumes, what you can do is to synthesize a fake T1 and then solve a much easier intramodality registration problem. So, of course, like I said, the problem is that you require this database of training data that has to be perfectly aligned. In our case, with the histology and the MR, that's never the case. So our first attempt to solve this problem was, okay, thinking, we know that synthesis can improve registration, but requires aligned data. But registration actually aligns data, right? So can we solve both of them simultaneously? So we proposed a probabilistic model for this, which is my approach to almost every problem in life. It's a very simple model where you say, well, I start from my MRI, there is some linear registration, and then there is an intensity warping that gives me my block phase, and another intensity warping plus a non-linear deformation, that gives me my histology. And if you want, you can include some landmarks to try to help the registration like I did before, but you don't have to. Then you can solve. You can use Bayesian inference and trying to estimate the most likely registration that led to this, to this data that you observed. If we register one, so independently, and I know that this doesn't make any sense, I'll go back to this, but if you register each MR slice and histosection independently, this is data from the Allen Institute, this is publicly available data, you get something that looks like this using mutual information, and if you use the joint model, it gets prettier. It's still far from perfect, and it's a bit jagged if you look at it, again, because you're doing every slice independently, but it definitely gets better. This is an axial view. If you look, for example, at the thalamus or the putamen here, cortical regions, they also get much cleaner. Same thing with this is the big brain, the data from Germany, from Jülich. I have boxes in the areas where things seem to improve the most. This is before and after. This one, before and after. So it's not perfect, but it gets much better. This was working fine. It's very slow, but we don't care too much for that because we can just run it overnight. We don't care, right? But still, we cannot really ignore all the advances in deep learning. I'm actually very interested in all these new machine learning methods. And there is this paper that came out in 2017, which was like pretty much exactly what we needed, right? So there's this cycle gang model that I really like. I don't know if you've seen the paper. It's the results are very pretty, very spectacular. So the idea is you give me 100 pictures of zebras and 200 pictures of horses, whatever, but they are not matched. They're not aligned, right? There's no way you could get a zebra to be exactly in the same pose and shape as a horse. Same thing with, for example, photographs and paintings, and it does a really good job mapping from one modality to the other. My favorite is probably going from photographs to paintings. This is a Monet. It's pretty cool, actually. And it's great because it's exactly what we needed, right? Like we don't have aligned data, which is the case of this model. The idea is very interesting, I think. This looks a bit of a mess, but it's actually very simple. The idea is that if you start, let's say that modality A is my horse, right? So I have a machine which turns horses into zebras. So you get a fake zebra. I'm following the blue arrow at the moment. And I can take my fake zebra, feed it through another network that turns zebras into horses, and I get a double fake horse, right? So I can compare my double fake horse with the original horse and hope that they look alike. And then I can go the other way around. I can start from a real zebra, make it a fake horse, and then a double fake zebra, compare with the original one, and they should be similar, right? So I can minimize these two losses, and you would think that that could work right away, but it doesn't. And the reason is that I could start from a horse, generate noise, and then because the network has so much flexibility, I can overfit and recover my original horse, right? That's technically possible. Like I could synthesize, I don't know, a car from the horse and still recover the horse. But what you do to prevent this from happening is you add a discriminator here and another one here that is trying to tell apart real horses from fake horses. So if I take real zebras from fake zebras. So if I take, for example, a real horse, I generate a fake zebra that does not look like a zebra, this guy, the discriminator, is going to call it out. So it's a very clever idea, and it works pretty well, at least with horses and zebras and monets and photographs. The problem in our case, when I saw this paper, the code is publicly available. I'm very excited. I install it. I run it on my data. And then the problem we had is that this CycleGang, the discriminator, for example, is really good at texture, right? Like you give me a zebra, and like, telling apart a zebra from a horse, great. But the problem is that if you give me a zebra and I flip the contrast of the stripes, so I switch black for white, it's still a zebra, right? But if you do that with the cerebellum, you are in trouble. So that didn't work right away. But then I was very, very lucky that our collaborator, Bennett Landman from Vanderbilt, he happened to be in London. I was showing him this, and I was like, man, I have exactly what you need. So this is work by his student, Yuan Kai Hua. And the problem was a bit different, but essentially they took the CycleGang model, and what they wanted to do was to say, okay, I have MR and CT, and I want to learn how to segment CT from the MR. So the idea is, okay, if you give me the MR and I synthesize my CT, I want to train a net that gives segmentations that are similar to the manual segmentations you had on the MR. And I'm like, okay, but I don't want to segment anything here. And he was like, it doesn't matter, because this segmentation problem, like if you solve for if you're trying to segment the white and the gray matter in the cerebellum, if you flip the contrast, that segmentation is not going to work. So indirectly, you're going to be regularizing. So it was a good idea. We tried it. It didn't work at first, of course. But it turns out that with some tweaking, and this still work in progress, but we took this network, we symmetrized it. And even with like automated segmentations that we computed using SPM, because we don't want to have to manually label anything, the synthesis gets much better. So I don't have any quantitative results yet, but again, my postdoc Matteo Mancini is working on this, and hopefully at some point I can show you cooler results. The other thing that we are trying to automatize is the 3D reconstruction. And I was saying earlier that for the Allen dataset and the big brain, you're doing like this, or I was sharing results where we're doing all the registrations independently. So you're saying, okay, you give me a historical section, this is the plane in the MR, and I try to register one to the other. But that doesn't seem to make much sense, right? Like this registration should not be independent. I know that whatever I get should be smooth, right? Which wasn't the case before. The problem is that, well, what you can do, right, is to achieve, you can achieve smoother reconstructions if I take the histology and I register each section to the neighbors. And then, yes, you get something that is very smooth and looks nice. The problem is that you get this, well, you have two problems. One is the set shift, which is essentially the drift, the accumulation of errors. So if you, for example, start with a cylinder, but you start accumulating errors, you end up drifting. And the other one is the infamous banana effect, which is essentially if you have a curved structure and you slice it and then you register each plane to the neighbors, you end up with a cylinder. So I actually have a little animation here. So you start from a banana. I also have an example with a hippocampus. Even though it's MR, I can still illustrate the problem. I can slice it, right? So I can artificially distort every coronal slice in this MR of the hippocampus. And then I can register each one to the neighbors, and I end up with this, right? So it looks pretty. If I look at this, if I didn't know what a hippocampus looks like, I could buy this reconstruction here. But of course, we're not happy about this. But what we can do actually is use the registrations of neighboring slices in the MR to undo this banana effect. That sounds a bit counterintuitive and a bit weird in the sense that, well, if you give me an MR volume, it's already smooth, right? It's already 3D consistent. Why do I register each slice to the neighbors? But actually, that's very, very important, because if you have a banana or a hippocampus and you compute these registrations, if you invert them, that enables you to, I guess this is a word, de-bananify and bananify the histology. So, I mean, it's a bit more, it's not exactly that, it's a bit more sophisticated than that, but the idea is that you assume that you have this set of like hidden transforms. It's essentially a spanning tree that interconnects all your data. So this is a stack of histo sections, and this is a stack of MR slices. And essentially any spanning tree works, but we use this one where we have like, T1 is connecting slice 1 to section 1, T2, so forth until Tn. And then we have this Tn plus 1, n plus 2, and so on, interconnecting all the MR. So any pair of images is connected in this graph. And then the idea is that if you, for example, register this guy to this guy, this is nothing but a noisy measurement of the true underlying transform, which would be the inverse of T1 concatenated with Tn plus 1 concatenated with T2. And then the idea is, okay, you give me a bunch of registrations, which are noisy measurements, and I can use Bayesian inference to try to figure out what's the most likely configuration of these hidden transforms, right? In practice, I mean, in theory, you could register everything to everything. You could register the, if you're, I mean, this is completely crazy, but you could register the first MR slice to the last histo section, theoretically. But in practice, we register across modalities, like right across, like essentially, this guy to this guy, this guy to this guy. And we register each section and each slice to the two nearest neighbors, or 2, 3, or 1. Up to you, but a limited number. And then you can use, like I said, Bayesian inference. In what we observed in synthetic data is that in the beginning things get better, but if you use too many neighbors, you start over smoothing. So there seems to be a sweet spot. This is something I want to look into because I'm pretty sure we can improve this. But yeah, this is our construction. If this is, again, we pretend that T1 is our MRI and the T2 is the histology, because otherwise there's no ground truth, right? We artificially distort the T2, and then we try to reconstruct. So if you use 0 neighbors, which is essentially just, by the way, this is using mutual information. I fine-tuned like the parameters of registration to death. And this is the best that I could get, what you see here. And it gets, I don't know if you see it very well on the screen, but it gets much prettier when you use the framework. So let me show you another example. This is real data from the Allen. This is before and this is after. So if you look at areas, for example, I don't know, like down here, this cortical region or the cerebellum, or actually the hippocampus gets, let's go back and forth. It gets much cleaner. And the nice thing about it too is that this is independent from improving the 2D registration, right? So it's orthogonal. We can put this on top of this registration using synthesis. This is another example from the Allen, looking at how the segmentations get reconstructed. It gets much cleaner. Another example from here, this data from Caroline Magnan, also gets prettier. And the last thing I wanted to go over is the manual segmentation process, which is a complete nightmare if you have to do it entirely by hand. And the first thing that we're wondering is, can we get away with labeling one slice every n, right? Does it make, because they're going to be so similar to each other. If you're labeling every 100, 200 microns, is it really worth it, right? So there is this paper that I really like. It's like the smart scissors in Photoshop, where you essentially say like, I want to, I give you a point here, and then it automatically finds the shortest path that connects the 2 points while following edges. So it's essentially the 3D version of that. And the idea is that you give me like a contour in one slice up here, the contour of the same structures down here, and can I come up with these surfaces that connect these two sets of contours optimally. So Leo Grady, who used to be in Boston, I believe, he has this fantastic algorithm to do this in the binary case. So we actually extended it to the multi-label case, where you essentially you constrain these surfaces not to intersect each other or not to leave gaps in between. And it does a pretty good job, actually. This is like MR data. We also tried running his algorithm one label at a time and then solving these conflicts with some ad hoc rules. But it turns out that when you use the couple framework, sometimes structures with high contrast, like for example the putamen, help you recover structures that don't have a lot of contrast, like the palindrome, which is lost here, which is cool. It's another example using hippocampal subfields, and quantitatively you can show that you can do a better job if you consider them simultaneously. The small problem with this is that the coupling terms like that make sure that these surfaces don't overlap or are not disjoint. Prevent you from rewriting the problem as a minimum cost flow problem, which is what Leo Grady did to make it super efficient. So this takes forever to run. So I left it aside for the time being. Another problem for the histology is that it requires 3D consistency, so the reconstruction has to be good to be able to use it. Another solution that we tried, and this is work by my PhD student Alessia Tseni, is combining two of the most successful segmentation models in brain imaging, which is multi-atlas segmentation and deep learning. It turns out that multi-atlas is really good in the sections nearby because the registration of neighboring sections is pretty good. But when you go further away, training a network does a better job. So you can actually use both of them simultaneously, combine into a probabilistic model, and you can get the best of both worlds. This is what I was telling you about, right? Like the CNN, if you are close, the label fusion does better, multi-atlas segmentation. If you're far away, the CNN does better, and you can again combine them pretty nicely. Running out of time, so I'm just going to jump over to discussion and future work. Like I said earlier, we're still in month 28 of the project. In London, we are doing things a bit better. You still see the checkerboard patterns, but we learned from the mistakes in Spain. We are being a bit smarter about how we acquire the data. We're taking photographs of the slices too, which is super useful to initialize the registration. Data looks prettier than in Spain, which is good. We are generating a lot, like an insane amount of sections. And I want to show you a reconstruction I put together a couple of months ago. We still don't have a whole brain yet, which is a bit of a shame. But this is what you get when you put together essentially the synthesis for the 2D registration and the 3D framework on top. So this is just a block of the cerebellum. And if you look at the cerebellum is sectioned sagittally, and these are the axial and coronal reconstructions. So hopefully I'll be able to show this for the whole brain at some point. So very quickly, extensions. We really want to use diffusion MR in the likelihood term. I'm trying to drag Anastasia to help me with this and write a grant about it, because it's a bit crazy to, for example, try to segment the thalamus looking only at the structural images, right? We also want to look at other smarter ways of interpreting segmentations, maybe making these optimal surfaces interactive. So yeah, I'm trying to convince Hui and Morgan. They're being super nice. Like they sent me already some data, and we're hopefully going to play with this together and get it to work. There is also we've been looking into how to interpolate these segmentations, but it's also useful to try to semi-automatize the segmentation of a single slice, make it interactive. So I'm actually have a meeting with Rob Peng later because Bruce has been very interested for a long time, and I totally agree that this is a must of having this type of techniques in FreeView. There is also the problem of how to bridge resolution gaps in this patient segmentation, because we're going to have these atlases at super high resolution, but then you want to apply it to in vivo scans, right? I'm collaborating with Koen van Limput, who's still affiliated to the Martinez and comes once in a while to try to solve this. And of course, like I said earlier, anything you might come up with or you're interested in, I'm very open to chatting with you. Like I said earlier, I'm here 1 day a week. These are my emails. So yeah, please don't hesitate to contact me if you saw something interesting. And of course, thanks to these people who are crazy enough to give us money to play with this data. And especially, of course, like my team and all my collaborators, which is, I mean, the best part about being in science, right? Is the people you get to work with. And yeah, that's it. Thank you for your attention.